In this video, I want to prove to you that if you have a connected graph with n vertices and you know it has n-1 edges, then it must be a tree. Okay, so we have our definition of tree, which is that it's connected and it has no circuits. And now this is giving you another way to recognize when you have a tree. It's connected and it has n-1 edges. So you don't need to check for circuits. We just need to count the number of edges. Okay. So let's see how this goes. Let's suppose, so let G be one of these things, connected. This is a connected graph with n vertices and n-1 edges. So it's already connected. We just need to show that it can't have any circuits. Okay, so to show that G is a tree, we'll show it has no circuits. We'll show it has no circuits, and we'll use contradiction. Okay, so assume for contradiction that G does have a circuit, that G does have, circuit. Okay, so I claim that if we remove an edge, maybe call it UV, from a circuit, the remaining graph is still connected. So if we remove an edge UV from a circuit, the remaining graph must be connected. Why? Because if we have why do we still have a walk from U to V? Well, the edge UV was part of some big circuit, and instead of taking the edge from U to V, I could just go the other way around the circuit. Okay, it must be connected because any walk from any walk using the edge U to V, so any walk between two vertices that's using the edge UV could just go the other way around this circuit. Okay, so for example, and here this is another sort of in parentheses kind of proof. For example, suppose I had a graph, maybe the graph looks like this hourglass, and this is my edge UV. If I take this edge out and I have a walk from between two vertices that uses that edge, like suppose I have a walk, suppose I were walking from U to, like, I don't know, this vertex W over here. If I had been going like this, maybe in green, U to V to W, instead, I would go the other way around the circuit. So there's the circuit goes from U, V, W like this. There's a circuit that goes around this way. And so instead of walking from U, V to W, I would go this way to get to W, the other way around the circuit, okay? So you have to sort of convince yourself of that. All right, so, so now, then let G1 be the graph that's equal to G. It's a subgraph of G where I take away an edge in one of the circuits of G, okay? So I know it's still connected, and then I say, well, if my new graph still has a circuit, do it again. So if G1 has a circuit, I'm gonna break that circuit too. So I'm gonna say if G1 has a circuit, I'm gonna let G2 equal to G1 minus some edge in a circuit. And I'm going to continue in this way. So continue in this way, where if I remove an edge, I break a circuit. If my graph still has circuit, I'll break another circuit until we arrive at, oops, a graph that I'll call GK that has no circuits. I mean, I can't do this forever, right? I had a graph, my graph that I started out with was finite. So, you know, I can only remove so many edges before I don't have any edges left at all. Okay. So then how many edges does GK have? Well, the graph GK has, well, I started with how many edges? Let me just put this on pause for a second. Oh, I started with n-1 edges, right? That was my hypothesis. Has n-1 edges. And then every time I up k by 1, I subtract an edge. So this has n-1 minus k edges. And is connected. Each one of these GKs is connected because I was only breaking cycles. But now this is a contradiction. This is a contradiction because if G is a connected graph and now it has no circuits, so GK is connected and has no circuits, so by the previous theorem, it must be that GK has n-1 edges, but because we started with n-1 edges and we removed some, we have fewer than n-1 edges, okay? So this is a contradiction. This is a contradiction if k is greater than or equal to 1, i.e. if G had any circuits. So therefore, G has no circuits and must be a tree. Okay, and that's enough for this one.